Our next topic is eigenvalues and eigenvectors. This is quite an important mathematical subject. I suggest you set aside a little bit of extra time to get it straight. I'm going to begin by recalling some basic setup about vector spaces and bases and things. So we have a vector space with a basis v1 through vn and a linear transformation from v to itself. And given all of this, we get the matrix of this linear transformation, and the important thing is it's with respect to this basis. And I'll remind you what that means. So you take the ith vector, say, and you write t of vi as a linear combination of the vj's, and then you put those coordinates into the ith column of the matrix. And that's the matrix that you get, and of course it depends on your choice of basis. So let's look at an example to refresh our memory. Suppose the vector space was two-dimensional, and this was our linear transformation with these coefficients a, b, c, and d. Well, according to the recipe I just gave you, you should take this a, b, and just put them in the first column, and c, d in the second. Well, of course, we're mainly interested in Rn, so let's think about what this means for the standard basis in Rn a little bit. So when you write down a matrix A, B, C, D, and you don't specify a basis, well, that means you're talking about the standard basis. So what does that mean? I want to look at this in view of the preceding discussion. So, well, you all know what the matrix A, B, C, D means. You know how to multiply. For example, it takes the vector 1, 0 to the vector A, B. And it takes the vector 0, 1 to the vector C, D. And what I'm saying is that from the point of view above, what this is saying is that this is taking the standard basis vector E1 to the vector AB, which is AE1 plus BE2. And it's taking the standard basis vector E2 to CE1 plus DE2. And according to the prescription above, I took the A, B and made them the first column, and C, D and made them the second. Okay, so that's just a little bit of reminder about how the matrix with respect to an arbitrary basis works. All right, now, in some sense, one of the main points here is I want to talk about the simplest matrices possible. So in a lot of ways, the simplest matrix is a diagonal matrix, A1 through AN on the diagonal. Such a matrix is very easy to understand. And, well, if the standard basis is E1 through EN, let's just do n is equal to 3. This diagonal matrix, it's saying, well, it takes the vector 1, 0, 0 to A1, 0, 0. And that's A1 times the vector itself. And similarly, it's taking 0, 1, 0 to 0, A2, 0, which is to say A2 times 0, 1, 0. And finally, it's taking 0, 0, 1 to A3 times 0, 0, 1. So what I'm trying to point out here is that the way to think of a diagonal matrix is that it's stretching these vectors by different amounts. It's stretching E1 by A1, and E2 by factor A2, and E3 is getting stretched by factor A3. And that's very easy to understand. You can draw a picture of such a thing. And you think of it as being stretching or contracting in these directions. Okay, so one of the main points of all of this is just the following observation or question: what is so special about the standard basis? We're all very used to thinking about it, and it's certainly an important basis, but there are other bases, and suppose instead of having a linear transformation which stretched in each of the basic directions, A1 in the E1 direction through AN in the EN direction, well, what if I had a linear transformation which did the same thing except with respect to some different basis? Well, there certainly are such things. And in a lot of ways, they're just as simple as an ordinary diagonal matrix. It's just you have to think about this other basis. And that is to say, T is still a simple operation. It's stretching or contracting in these different directions. And let's draw a simple picture of a simple example. Suppose I had two more or less random vectors v1 and v2. And suppose your linear transformation was multiplying by 2 in the v1 direction. And suppose it was dividing by 2 in the v2 direction. Well, that's a pretty simple linear transformation to understand. And so I want to be able to think about this almost as easily as I can think about an ordinary diagonal matrix. And this is the whole point of eigenvectors and eigenvalues. That's exactly what they do for you. They allow you to think of such a linear transformation as a diagonal matrix. So I'm going to state this as a question. Suppose you have a vector space with a linear transformation, and our vector space is always going to be Rn. A natural question is to try and find a nice basis of the vector space, v1 through vn, so that the matrix of the linear transformation with respect to that basis is as simple as possible, and the simplest that it could possibly be is diagonal. So you're looking for vectors vi such that tvi is equal to aivi, so that the matrix with respect to that basis becomes this diagonal matrix. Then I would consider this basis v1 through vn to be the best basis to use to understand this linear transformation. It might be better than the standard basis e1 through en. So let's look at an example of this. Suppose A was this matrix, 0, 1, minus 2, 3 in the standard basis. That's not a particularly nice matrix. I can't really picture what it's doing. It takes 1, 0 to 0, minus 2 and 0, 1 to 1, 3. And if you draw it, it's a little obscure. So you say to yourself, maybe there's a better basis to use where it'll be clearer what this linear transformation is doing. And notice that if you apply this matrix to 1, 1, it takes it to itself. And if you apply it to the vector 1, 2, it takes it to the vector 2, 4, which is to say 1, 1 is 1 times itself, and 2, 4 is 2 times 1, 2. So this vector stretches 1, 1 by a factor of 1, and it stretches the vector 1, 2 by a factor of 2. So with respect to this basis, this is a rather nice basis to picture the linear transformation. Here are these two vectors 1, 1 and 1, 2, and it's simply stretching by a factor of 2 in the 1, 2 direction, and keeping the stretch of a factor of 1, so to speak, in the 1, 1 direction. All right, so here are these equations that I had, and the conclusion is that if I chose this basis, v1 and v2, then the matrix with respect to this basis is, of course, very simple. That is the diagonal matrix. Okay, so that was a summary of really all the main ideas behind eigenvalues and eigenvectors. So let's go back and say things a little more carefully. So suppose you have an n by n matrix, and suppose you also have a vector v and a scalar lambda. And these have the property that AV is equal to lambda V. It stretches v by a factor of lambda. Then you say v is an eigenvector, or a lambda eigenvector, with corresponding eigenvalue lambda. So v is an eigenvector and lambda is an eigenvalue. And here's sort of the main theorem of all of this. Suppose you have an n by n matrix. And suppose A has n linearly independent eigenvectors. So let's call them v1 through vn, and write down their corresponding eigenvalues, lambda 1 through lambda n. Well, then, with respect to this basis, v1 through vn, the matrix of A is diagonal, with lambdas down the diagonal. And I want to emphasize that I've hardly said anything here. This theorem is obvious. It's just writing down the fact that A vi is equal to lambda I vi. But I've written it to emphasize the fact that having n linearly independent eigenvectors is the same thing as making the matrix diagonal. Okay, so that's all fine and good. It's great if you have a bunch of eigenvectors like that, but how do you find them? So here's an n by n matrix. How on earth do you tell if it has such a set of eigenvectors? So you're looking for vectors which satisfy this. AV is equal to lambda v. You want to solve this equation. Now the problem is v appears on both sides of this equation. So this isn't your standard linear algebra thing where we're trying to solve AV is equal to W, where W is fixed. It's a little trickier because v is on both sides. And not to mention the fact that we don't know what lambda is. So you've really got two unknowns, the vector v and the scalar lambda. Well, here's the idea. Let's get the v on the other side. Write this as AV minus lambda v is equal to 0. And write lambda v as lambda times the identity times v. And then combine a and lambda I to get a minus lambda times the identity applied to v is equal to 0. Now this is a beautiful equation. One of the key points is that the v is only on one side now. So this looks more like the kind of thing we know how to solve. And it's got the fixed vector 0 on the right. But let's address this issue. We don't know lambda, and here's the key. This equation is going to tell us lambda. So how does that work? So we're looking at this equation. How does this equation tell you what lambda has to be? Well, the key point is that this equation is saying that v is in the null space of this matrix A minus lambda I. And, well, so does this matrix A minus lambda I have a non-trivial null space? Anything besides the 0 vector in it? Well, we know how to tell that. It does if and only if the determinant of this matrix is equal to 0. There you go. This equation is the key. This tells you what lambda is. You write down this equation and you solve it for lambda. So basically we just prove the following theorem or algorithm. It's really both. Suppose you have an n by n matrix. Then lambda is an eigenvalue of that matrix if and only if the determinant of A minus lambda I is 0. Secondly, if you have such a lambda, then the lambda eigenvectors are exactly the null space of this matrix A minus lambda I. So that is something that we can do. So let's go back and look at our earlier example. I had this matrix 0, 0, 1, minus 2, 3. How do I find the eigenvalues and eigenvectors of this matrix? Well, A minus lambda I is this matrix minus lambda on the diagonal, which is to say minus lambda 1, minus 2, 3 minus lambda. Take the determinant of this matrix. You get determinant of this thing. That is to say minus lambda times 3 minus lambda plus 2. And that's a polynomial in this indeterminate lambda. So let's solve. Minus lambda 3 minus lambda plus 2 is equal to 0. That's a quadratic equation. Lambda squared minus 3 lambda plus 2 equals 0. And that factors into lambda minus 1 times lambda minus 2. There you go. We just found these two eigenvalues, 1 and 2. Okay, so let's go back and find the corresponding eigenvectors. Let's take lambda equals 1 first, find the 1 eigenvector. So you plug 1 into this A minus lambda I to get minus 1, 1, minus 2, 2. And you're looking for the null space of this matrix. Notice it has determinant 0, and it has a one-dimensional null space. When you solve this equation, you get, for example, x equals y equals 1. That's the basis of the null space. And similarly, when you go to find the 2 eigenvector, you plug in 2 into this equation and you get minus 2, 1, minus 2, 1. And the null space of this matrix is given by the vector. You solve this equation and the answer is 2 eigenvector is the vector 1, 2. So there you have it. I found the 2 eigenvalues, 1 and 2, and the 2 corresponding eigenvectors. So that illustrates the algorithm, and that's a good place to stop.